Selected excerpts from the MU-2 videos. All material is copyright 2015 by Holy Cows Incorporated. All rights reserved. Powerplant NTS.
The hollow main shaft runs through the engine and has the compressor and turbine sections mounted to it. This shaft is very rigid. Inside the main shaft is the torsional shaft. The torsional shaft transmits the power to the reduction gearbox, which drives the propeller. The main shaft and torsional shaft are connected together through splines at the rear of the engine only, so they are turning at the same speed. The torsional shaft is not as rigid as the main shaft, and can twist up to 11 degrees compared to the main shaft, based on the amount of torque present. The positive-negative torque sensor detects this angular difference. This angular displacement is converted into a linear displacement by the helical cut gears. When the torque is positive, the shaft and pilot valve moves in. And when the torque is negative, the shaft and pilot valve moves out. The oil inside the metering valve is regulated engine pressure oil. With no torque applied, the pilot valve is allowing most of the oil pressure to escape into the case, and the oil pressure within the metering valve is about 10 psi above the case pressure. At maximum torque, and therefore maximum displacement of the pilot valve has closed the discharge port slightly, which increases the pressure to just under 60 psi above case pressure. So, the relationship between the torque and the oil pressure can be determined. If we replace the fake pressure gauge shown here with a pressure transducer, the electrical signal can be sent to the cockpit and displayed as torque.
Engine start demonstrations.
Let's watch the normal start sequence uninterrupted, but with narration, and the focus coach spotlight on the instruments that you should be focused on. There is a lot going on in 60 seconds, so it is suggested that you watch this part several times, until you are comfortable with all of the steps. Using the thumb of your right hand, press and hold the unfeather pump switch. Observe the beta light comes on. With your right index finger, cover the starter switch. While maintaining focus on the beta light, press and hold the starter switch. Verify the beta light goes out with engine rotation. Above 10% RPM, observe jumps in fuel flow, and EGT, then release start switch. At 18 to 20%, beta light on, release unfeather switch, NTS test completed, power lever aft to above ground idle then hand to condition lever. Monitor speed is increasing at least 1% per second, and EGT does not exceed 700 degrees C. Beta light on steady by 40 to 50%. At 60% RPM, verify start light out, EGT drops, ignition light extinguishes, and engine stabilizes at idle.
Powerplant propeller.
Also contributing to the load on the speeder spring is the prop governor reset piston, found only on the slow turn engines. The speed setting shaft is mounted in the reset piston, which will move aft when high oil pressure is present. When it moves, it reduces the force on the speeder spring, which lowers the propeller governor set speed by 5 to 8%. All normal propeller speeds are calibrated in this condition. The significance of this will be discussed later. The metered oil pressure leaves the propeller governor, goes through the feather valve, and into the propeller pitch control. Since the beta tube is fully contained in the sleeve when in the propeller governor range, this metered oil pressure is sent through the beta tube to the propeller dome, which controls the propeller pitch.
Powerplant malfunctions.
There are 3 critical things to remember to do during an engine malfunction. First and foremost, fly the airplane. The next thing to remember is to fly the airplane. Finally, Don't forget to fly the airplane. Only after the airplane is under control and trimmed should you address the malfunctioning engine. These steps should be followed after an engine malfunction. Fly the airplane. Shut down the affected engine. First by identifying the affected engine. Then by moving the condition lever to emergency stop. Never retard the power lever to flight idle. Instead, move the power lever to the beta follow-up position, which is full forward. Propeller coupling failure. The first indication of a propeller coupling failure will be a yaw towards the affected engine. This will feel like an engine flameout, so react to the situation as such. As with any abnormal condition, the pilot should fly the airplane first. Once the aircraft is stabilized, we'll look at the gauges to determine what is wrong. The torque has fallen to 0. So did the engine flame out? The fuel flow has fallen slightly, but is still significant, and the engine speed is still up, so the engine is not flamed out. In fact, the engine is well over normal at 104%. These are all indications of a propeller coupling failure. It is not required to verify this, but if you were to look out the cockpit side window, you would see that the propeller is slowing or is already stopped, in the feathered position. So what just happened? Let's look at our pictures and schematics to see what is going on with the engine.
Fuel system, Module 3 of 4.
The fuel level control valve, located in the center main tank, controls the flow of fuel from the tip and outer tanks into the main center tank. This is a fuel level control valve, with the cover removed to show the float. The fuel valve is a hydraulically actuated shutoff valve, located in the center main tank. The fuel level control valve is located near the top of the main tank. Pressurized fuel from the tip or outer tanks is present at the lower inlet. A very small portion of this fuel is admitted to the upper surface of the diaphragm through a hole in the center of the diaphragm. With the fuel level in the main tank below the shutoff point, the pilot valve is open, and this fuel is allowed to escape past the pilot valve and flow into the tank, thereby relieving the pressure on the upper surface of the diaphragm. The pressure of the fuel on the lower side of the diaphragm pushes the diaphragm up, allowing large quantities of fuel to flow into the center main tank. When the float reaches the shutoff point, the pilot valve closes and stops the flow, so the pressure builds up on the upper surface of the diaphragm. The pressure per square inch above the diaphragm is the same as below it, but it is acting on a surface area approximately 5 times as large on the upper surface than on the lower surface, so the diaphragm is forced down and it closes, preventing fuel from entering the main center tank. This valve works the same regardless of the inlet pressure. Note that the fuel tank is not completely full when this valve closes.
Weight and balance.
When the airplane lifts off and the main wheels break ground, the point of rotation switches from the main wheels to the center of gravity. Since the change in longitudinal distance to the tail in the long-body MU-2 is small, there is relatively little change in the control position and force as the main gear leave the ground. Likewise on landing, when the point of rotation shifts from the CG to the main wheels, the distance is very small and therefore a relatively small moment is induced, so the nose wheel comes down, but not too hard. However, on the short-body MU-2, the gear is significantly further aft, about 40 inches behind the aft CG limit. This means that the moment caused by the weight is significantly higher, and the distance to the horizontal tail is significantly shorter, so a greater back pressure on the yoke is required to pull the short-body aircraft off the ground. Some control power is lost on landing when this arm shortens, so more control deflection is required.
End of MU-2 excerpts.